In this video, we're going to go through Wiens Law, otherwise known as Wiens displacement law. Given a star emits a black body spectrum as partially shown below, find A, the peak wavelength, B, the surface temperature in Kelvin, C, what color would our human eyes likely see the star as, and D, what bands of the electromagnetic spectrum are confirmed by the spectrum shown that the star emits. Let's go take a look at this. So we are given this spectrum based on observations. On the vertical axis, we have intensity, which is the amount of light being emitted. And on the horizontal axis, we have wavelength. Now, as mentioned in the given, we have a partial black body spectrum. So notice that the ends continue on both sides, the left and the right of the spectrum, and we're only given a partial center of the spectrum. We're given a little bit of the UV band, all of the V band, and a little bit of the infrared band. But clearly the graph goes on to the right and on to the left. We're only given a portion of the black body spectrum that's being emitted by this star. Now, the first thing we want to find is the peak wavelength. So peak means find the peak in the graph. So here's our V band, the entire band of the visual band of the electromagnetic spectrum, and notice that this star emits most of its light in the visual band. So we draw a line at the top where the peak is, and we can draw a line over to the horizontally across to where the intensity line is. And if we compare purple or violet light being emitted to the green light being emitted, we see that the star emits much more green light compared to violet light. So the peak occurs in the color green. Now, the peak of the wavelength, we just draw a horizontal line down, and we can label it based on the graph, and it's about 525 nanometers. So the first answer to the first question is, what is the peak wavelength? And the answer is about 525 nanometers. So I went ahead and put that in the solution section, 525 nanometers. Now, part B wants to know, what is the surface temperature of the star in units of Kelvin? To find the surface temperature, we need to know the equation Wiens Law, which is 0.0029 meter Kelvin, and that is equal to the wavelength maximum times the surface temperature. We already found the wavelength maximum. That is 525 nanometers. So now all we need to solve for is the surface temperature based on Wiens Law. The left side is already known. It is 0.0029 meter Kelvin, so we just need to carry that down. And then we need to substitute in for the wavelength maximum, and we're solving for the surface temperature. So I'm going to go ahead and solve in or substitute in for wavelength max of 525 nanometers. Now, 1 nanometer is 1 times 10 to the minus 9th meters. So we're going to have to multiply our 525 by 10 to the minus 9th to convert nanometers into meters. And then we just carry the other one down, which is the surface temperature. And I'm just going to label it surf to make it short instead of surface. So you can see I substituted in for wavelength maximum, and I just carried down the surface temperature. So all we need to do is divide both sides of the equation by 525 times 10 to the minus 9th meters. That would get rid of the 525 times 10 to the minus 9th meters on the right-hand side, leaving only the surface temperature left on the right-hand side. So we need to calculate out 0.0029 meter Kelvin divided by 525 times 10 to the minus 9th. So let's go to our Google calculator. So we need to put in 0.0029, and we want to divide that by 525 times 10 to the minus 9th. 525 EE minus 9, hit the equal sign, and we're given 5523, and then we see an 80 or an 81 over here, which is higher than 50, so it would be 5524 after we rounded it up. So we're going to put in here 5524. So the surface temperature of this star is around 5,524 Kelvin. Now we know the units are Kelvin because meter drops off in both sides of the equation. So I'll go ahead and switch my color so you can see it. Meter drops out, and we're only left with the units of Kelvin on the right-hand side. So the answer to part B is 5524 Kelvin for the surface temperature. So I'm just going to label this answer B right here. Now answer C is the answer to the question, what color would our human eyes likely see the star as? Well, we need to go back to our graph. Well, we wouldn't see it really as purple. So I'm going to go ahead and erase that. We wouldn't see it as purple. Now it emits a lot of green light, but notice over here the intense amount of red light being emitted. This object is emitting a lot of red with a little bit of orange and a little bit of yellow. So you're likely to see this object as more like an orangey red type star. So what color will our eyes likely see it as? And I'm just going to say orange red, because it's going to emit more orange and red colors than it is going to emit of green. So we're going to see it as orange-red. The other thing is that our eyes are so attuned to the color yellow that we are not likely to see this star as being green, even if it did emit green light. And we would see it mostly as yellow. But because in this case it emits so much more orange and red light compared to the amount of green light, we would see it mostly as this orangey red color. Question D says, what bands of the electromagnetic spectrum are confirmed by the spectrum shown that the star emits? Well, we can confirm ultraviolet, we can confirm the visual band, and we can confirm the infrared band. Those are the only three ones that we can confirm. So I'm going to put answer D here is IR, V, and UV. Those are the three bands that we can confirm. So we have A, B, and here's answer C. Out of our 4 questions, we have 4 answers on Wiens Law.